Hello everyone, my name is Federico Barbacovi and I'm a PhD student at UCL. The title for this mini presentation is Spherical Functors and the Flop-Flop Autoequivalence, which is also the title of a preprint I uploaded on the archive about a month ago. What we're going to talk about today is the homological algebra picture related to the birational geometry picture of flops. So what's a flop? A flop is a map from two schemes, x minus and y, which is a small extremal contraction. I'm not going to define what's a small extremal contraction, but the idea is that a map, which is birational, it contracts something of codimension bigger or equal than 2, and it has some properties, in particular related to the canonical bundle of x minus. A flop of f minus is a map from x plus to y, which we call f plus. It has some similar properties to f minus. The example to have in mind is when x minus and x plus are birational Calabi-Yau, then they're automatically related by a flop. To this birational geometry picture, we have an homological algebra picture, which goes as follows. If X is a Noetherian scheme, then we consider the bounded derived category of coherent sheaves on X. And the conjecture is that if X minus and X plus are related by a flop, then the bounded derived category of X minus is equivalent to the bounded derived category of X plus. Here we're talking about triangulated categories. This is a very interesting conjecture, but it's very problematic to tackle it because the first question we have is where do we get the equivalence? An easy thing one could try to do is to use the fiber product. So we take the relative fiber product of x minus and x plus respect to y, and we try to see whether the pull-up, push-down functors q pull-up, p push-down, or p pull-up, p push-down are equivalences. As a side remark, these functors are derived. I'm not writing left or right derived functors to ease notation. If these functors are equivalences, but let me remark that this is not always the case, even if it is often enough, then we get the flop-flop autoequivalence, which is just pull-up, push-down, pull-up, push-down. We can consider it for either side. We're going to consider it for x plus. This autoequivalence is built in the geometry of this picture of the flop-flop, of the flop situation. So it's interesting to study. If we recall, the title of the presentation is Spherical Functors and the Flop-Flop Autoequivalence. So now we have introduced the Flop-Flop Autoequivalence. What we have to do is to introduce the spherical functors. So let me give you a very short guide to spherical functors. So we have a functor from a category C to a category D that has a right adjoint FR, and we suppose that C and D are triangulated. And we would like to have a procedure that gives us an autoequivalence of D when we start with such a functor F. And the thing we can do, we can consider the cone of the counit mapped from F composed with FR to the identity, and we call this the twist round F. Of course, this won't produce in general an autoequivalence, but if S is spherical, then the twist round F is an autoequivalence. So in this way, given a particular functor, we can produce an autoequivalence of the target category for this functor, which we call the twist round the functor F. The question is, why is this interesting? What's the difference between having a normal autoequivalence and the twist round a spherical factor? Well, the point is that if C has what's called a semi-orthogonal decomposition, which is just a way of splitting up C into two subcategories in such a way that there are homes only in one direction, and F satisfies some mild technical conditions, then the twist round F splits as the composition of the twist of F restricted to A composed with the twist of F restricted to B. And this is a theorem proved by Daniel Alpert, Leisner, and Shipman. And so understanding C can help us in understanding the twist round F. And the point is that the first theorem I'm going to state, which is in the paper I talked about before is that the flop-flop autoequivalence can be realized as the inverse of the spherical twist around the spherical functor given by push down to the bounded derived category of X plus from the quotient of the kernel category for the push down by a P by the common kernel for the true functors. The interesting part of this statement is not that the functor can be realized as the inverse of a spherical twist, because there's a very general theorem proved by Ed Siegel that says that basically this can always be achieved. The point here is that the source category is built in the geometry because it's a subcategory of the quotient category of the fiber product modulo the common kernel. And this is interesting because we have a geometric source category. And we want to understand this category. So the question now becomes, what can we say about this source category C? And to understand what we can say, let's look at the example of standard flops. So in this picture, X minus and X plus are the total space of n plus 1 copies of O minus 1 over Pn. And Y is the affinization, so it's the spectrum of the H naught of the structure sheaf of either X plus or X minus. In this picture, X plus and X minus are actually equal, so they are isomorphic, and therefore, usually they are derived equivalent. The point is that they are not isomorphic relative to Y, and that's why it's interesting to look at standard flops for the flop autoequivalence and the picture, the homological algebra picture. The affinization maps from X plus or X minus to Y contract the zero section and are isomorphism outside it, as X plus and X minus are birational Calabi-Yau because of the way we chose the line bundle and the number of copies. Then we are in the flop-flop situation as above. And so we can take the fiber product relative to Y, which in this case is identified with the total space of O minus 1 over Pn cross Pn, and look at the push-pull functors. These are equivalences, and this was proved by Ondal and Orlov. And by Addington, Donovan, and Michan, it was proved that the flop-flop autoequivalence splits as the composition of n inverses of spherical twists around spherical objects, which were introduced by Seidel and Thomas. In the picture we had before of spherical functors, these are spherical twists around the spherical functors whose source category is the bounded derived category of finite dimensional vector spaces, and the functor is given just by tensor product with the object I wrote down here. So there are n functors. And here comes another theorem I proved in a paper, in a different preprint, which says that if you take two spherical functors f and g with the same target category C, then there always exists a category D and a spherical functor out of D with target category C, such that the twist around this new spherical functor is a composition of the twist around the two previous spherical functors, and the source category D has a similar orthogonal decomposition in terms of the source categories for the spherical functors G and F. The point is that, as before, we have this isomorphism that tells us that this flop-flop autoequivalence is a composition of many inverses of spherical twists. We'd like to see whether this picture is reflected in the geometry we had before. So if the source category has a similar orthogonal decomposition that respects this theorem here. And the theorem in the paper on spherical functors and the flop-flop equivalence says exactly that in the standard flop fixture, the source category for the spherical functor has a similar orthogonal decomposition in terms of n copies of the bounded derived category vector spaces, where the ith copy from right to left is generated by the structure sheaf of Pn cross Pn twisted by 0 minus I. So we get exactly a description which fits with the theorem that lets us construct composition of spherical twists as the spherical twist around a single spherical functor. And it's also geometric because the generators for the single pieces of the SOD are given exactly by the structure sheaves of Pn cross Pn, twisted in the correct way to get the spherical objects we have here, OPN twisted by -1 till OPN twisted by -n, because I here goes from 1 to n. This is only one example. The theorem works in a very big generality, so you can get also other examples. For example, Mukai flops, Abua flop, Grassmannian flops. The point is, what's a nice description of this source category? And we still don't have a comprehensive answer in general, so we'll take all step by step, example by example. Thank you very much for your attention. And here are the references I talked about before, if you want to look up some of the things I was talking about.